For several decades, we have been hoping that we could harness the immune system to control cancer. In this video, I will discuss some of the progress that we have made. My name is Dr. David Stewart. I'm a medical oncologist in Ottawa, Canada, and a professor of medicine at the University of Ottawa. And I recently wrote a book on cancer intended for patients called A Short Primer on Why Cancer Still Sucks that can be purchased if you're interested through Amazon Books. This is the 8th out of 16 videos I'm preparing to discuss different topics that people ask me about cancer. And for additional details, you can see my book. Importantly, for your own personal health care, rely on your own healthcare providers for any advice. Your immune system is designed to protect you against dangerous invaders like bacteria and viruses. And it can also protect you against cancer as well. But cancers can develop if the cancer cells manage to evade the immune system. The immune system is quite complex. Here, I will only present a very simplified version of part of it. But essentially, cancers can develop if there's a defect in the immune system or if the cancer develops defenses that enable it to survive attack by the immune system. I will first discuss how your immune system can recognize a cancer. Your cell breaks down old proteins over time to replace them with new proteins. The proteins are broken down, the old proteins are broken down through a mechanism called the proteasome, and that breaks them down into peptides. When those peptides are formed, then they may be attached to another molecule called a human leukocyte antigen. And those human leukocyte antigens can then bind to other molecules that together form what is called the major histocompatibility complex, or the antigen presenting machinery. The antigen presenting machinery carries the peptide to the cell surface and presents it to the immune system. If the immune system recognizes that something as being normal, part of you, part of self, then it does nothing more. But if it recognizes it as being abnormal, something that should not be present in you, then it brings in other cells to mount an immune defense to kill the cells that are producing that peptide. Abnormal proteins that stimulate an immune response are called neoantigens. And in response to them, T cells are developed that can then kill cells that display the neoantigens. Cancers develop because of mutations, so that with the mutations, abnormal proteins are formed. They are what form the abnormal peptides that are recognized as being neoantigens. But many cancer cells, one of the very first things that is mutated is actually the components of the antigen presenting machinery, or it's malfunctioning in some way. So those peptides are not carried to the surface of the cell, so the immune system does not recognize the cancer cell, the developing cancer cell, as being abnormal. On the flip side, for some cells, the neoantigen is carried to the surface of the cell, but then the tumor cell develops defenses to protect it from being attacked by the immune system. These mechanisms that tumor cells use to keep themselves from being attacked are very similar to what your normal cells use to protect themselves from being attacked by the immune system. These are called immune checkpoints, and they are very, very important to keep you from being destroyed by your own immune system. And so far, we have identified 13 different immune checkpoints that are present in human cells. One particularly important one is the PD-1, PD-L1 system. PD-1 is located on immune T cells, and PD-L1 is present on your normal cells. When a T cell comes in close to a normal cell, then the PD-L1 on the normal cell interacts with the PD-1 on the T cell to turn the T cell off so it does not kill the cell that displays the PD-L1. In the early days of research on immunotherapy, researchers tried to really stimulate the immune system to get to produce more and more immune power to overcome cancers, but that didn't really work. But the discovery of the immune checkpoints led to a major step forward. Immune checkpoint inhibitors were then developed. So these are antibodies that bind to one part of the immune checkpoint to inactivate it. And again, one of the first ones to be developed were things that attack the PD-1, PD-L1 system. So drugs like nivolumab and pembrolizumab that bind to PD-1 to inactivate it, or drugs like atezolizumab and durvalumab that attach to PD-L1. And so if a monoclonal antibody attaches to either PD-1 or PD-L1, that prevents the interaction of PD-1 with PD-L1 so that the T cell, the immune cell, is not turned off so it can carry on to attack the cell. Across a wide range of types of cancers, these PD-1 or PD-L1 inhibitors can lead to major tumor regression in between 10 to 30% of patients with that malignancy. And with that tumor regression, there can be marked improvement in cancer symptoms as well as prolongation of life expectancy, sometimes by 4 or 5 years or more. Again, in some patients, the treatment does not work at all. In others, it can be a marked benefit for, as I said, for 4 or 5 years or more. Inhibition of the CTLA-4 immune checkpoint is also important. So with drugs like ipilimumab, that's particularly important for malignant melanoma, although it is of some value in a few other types of malignancies as well. Inhibitors of PD-1 and PD-L1 may be particularly effective against tumors that have very high expression of PD-L1 on the surface of the tumor cells. However, these inhibitors can even work in some patients where there's no PD-L1 expression, and they may not work in some patients even if the expression is very high. But generally speaking, the higher the expression of PD-L1, the higher the probability that these inhibitors will work to unleash the immune system against that cancer. Administering this type of immunotherapy before or after surgery or radiation that's given with curative intent for localized cancers can also increase the probability of long-term survival. So they're effective at eradicating small micrometastases or controlling them so that they do not show up to become incurable large metastases. With respect to other immune checkpoints, there's early data suggesting that another one called LAG-3, that treatments against it might be of value in some tumor types, and also another one called TIGIT, that active clinical trials are underway. And we expect that there will be much more work done in the not too distant future, exploring blockage of other immune checkpoints in the body. As a rule, the immune checkpoint inhibitors are well tolerated, as a rule, but not by all patients. Some patients have very serious toxicity. So some patients have no problem at all with them, but some can get a bit of inflammation of some tissues. Some patients can get very severe inflammation, including potentially life-threatening inflammation. So if we see any toxicity at all, what we see most commonly are things like rash or diarrhea because of involvement of the skin or the bowel. But there can also be very severe immune reactions against lung and heart and liver and kidney and just about any organ in the body in a small proportion of patients. With respect to why the toxicity is not even far worse than it is, it's been hypothesized that the immune checkpoints are most important to people very early on in life, and that later on in life they become far less important. So if they're inhibited by these immune checkpoint inhibitors, there may be minimal damage or minimal problem for normal tissues, but the cancer is still relying on being protected by these immune checkpoints, so the cancer itself may be preferentially targeted. There are also other ways of using the immune system to fight cancer. So one is to develop antibodies against cancer cells themselves. So typically a monoclonal antibody will be developed to target a substance on the surface of the cancer cell. And so, for example, the drug Herceptin or trastuzumab was designed to bind to something called HER2 or ERB2 on the surface of some breast cancer cells. And some breast cancers may have a greatly increased expression of HER2 or ERB2 because of what's called gene amplification, several extra copies of the gene for that protein, so it's very high expression. And then the monoclonal antibody may kill the cancer cells either by interfering with the cell division or else by attracting in other parts of the immune system to destroy the cell that overexpresses ERB2. There's also a lot of work to attach chemotherapy drugs to monoclonal antibodies. So then the monoclonal antibody carries the chemotherapy drug in close to the tumor cell and concentrates the chemotherapy drug in tumors that overexpress the target of the monoclonal antibody. So this combination of a chemotherapy drug attached to a monoclonal antibody, that's called an antibody drug conjugate. And one example of a useful one that has recently been developed is one called trastuzumab deruxtecan that again will target tumor cells that overexpress HER2 or ERB2. In some cases also, a radioactive molecule can be attached to a monoclonal antibody. So then the monoclonal antibody is being used to bring radioactivity in close to the tumor cells to concentrate the radioactivity there, so it preferentially kills tumor cells. There are also other increasingly sophisticated ways to use monoclonal antibodies. So, for example, the new drug amivantamab, one arm of the monoclonal antibody attaches to the epidermal growth factor receptor that may be overexpressed in tumor cells, and the other arm attaches to another growth factor receptor called MET or MET. And this has been successful at shrinking some kinds of cancers. In addition, a monoclonal antibody may be developed where one arm attaches to something on the surface of the tumor cell and the other arm attaches to an immune T cell. So this is a way of bringing immune T cells in close to tumor cells so that the immune T cells can kill the tumor cell. The monoclonal antibody bevacizumab binds to a protein circulating in the bloodstream called vascular endothelial growth factor. Vascular endothelial growth factor is important to tumors. They produce it to stimulate new blood vessel formation, and the cancer cannot grow without new blood vessel formation. So bevacizumab, by binding to vascular endothelial growth factor, prevents or decreases the formation of new blood vessels, and that limits the extent to which tumors can grow. So all of these approaches can be of some value to some patients. However, they do not cure any patients with advanced metastatic cancers, but they can improve symptoms and prolong life expectancy and are useful additions to our armamentarium. There's also very substantial interest in developing cancer vaccines. There's been a lot of work done over the past few decades trying to develop effective cancer vaccines, but they have not worked very well. However, there's great interest in the new technology, mRNA, that gained prominence in development of COVID vaccines. This technology can also be used to develop cancer vaccines, and early on it is showing great promise. The idea here is that if the cancer does not present a neoantigen to the immune system because the antigen presenting machinery is broken in the tumor cell, this is another way of presenting the neoadjuvant to the immune system to create a vaccine. And so once that vaccine is created, once the T cells are generated to recognize it, then those T cells can actually attack the tumor cells that have the abnormal protein. There's also been a lot of interest in what are called CAR T cells. CAR T cells are immune cells that are programmed to very specifically attack cells that express different neoantigens. And they've been particularly useful so far in some kinds of childhood leukemias and lymphomas. There are major challenges in developing them for other cancer types, but early promise that they may end up being quite useful. But the days are still early on. They are quite toxic, but again, a lot of research is underway to try to make them less toxic. There's also been interest in actually extracting immune cells or T cells that are infiltrating into tumors and then trying to grow them in the laboratory to produce a large number of them and then inject them back into patients. These are called tumor infiltrating lymphocytes, or TILs. And it's thought that if they're present in the tumor, they must be there because they recognize an antigen in the tumor. And if you can just give enough of them, that might be sufficient to kill the tumor. So there have been some early successes in small numbers of patients, but it's a very laborious, tedious exercise to produce this. But again, a lot of research underway to try to make it easier and more feasible. Back when I first started my oncology training, I had a lot of interest in immunotherapy. So this was in the late 1970s. But then what my impression was that there was a tremendous amount of hype and hyperbole and very little being accomplished with it. So I became very negative against immunotherapy in general. And that my negativity lasted until about 2014, 2015, when the early results started coming out with the PD-1, PD-L1 inhibitors. And these drugs were unequivocally of marked benefit in some patients with advanced metastatic cancers. And so since then, we have now recognized, I very much recognize that immunotherapy as a treatment modality of great importance for some patients with a lot of promise for the future. There are many challenges to overcome with it, but as long as research keeps on going, we will keep on making progress. So on this and other aspects of cancer and immunotherapy in particular and cancer in general, again, see my book, A Short Primer on Why Cancer Still Sucks, that can be purchased online through Amazon Books. I hope that you have found this video helpful. Thank you.